Hey, welcome back. In this lecture, we're going to be concluding our discussion of skip lists and then talking about bit vectors. Here in the local lecture, we also started hashing just a bit in lecture 24, but since it was only 5 minutes worth, I'm just going to put it at the beginning of lecture 25 for the videos instead. So for those of you remotely, I'm sure you don't care, but for those of you who are local and happen to be taking a look at these, I'm putting the hashing introduction on lecture 25. So for the remote folks, this will be a little bit shorter than normal, I expect, and the next one will be a little bit longer than normal just because I'm taking the ending 5 minutes and tacking it on. There's no sense spending 5 minutes only talking about a subject on a video. So where we left off was we had this skip list where we had the issue we were dealing with here was, actually, since I've got the other slides right in front of me, we had this. So Charles can save himself some work now. We had this slide in the last lecture that I just finished 5 minutes ago. And the problem here was not any sort of lookup. The problem was insert or remove, because we discussed in that lecture then the idea that sticking a value in here meant either rearranging all the pointers to keep it perfect, or instead having to shift all these values down, insert a new value here, and then shift the numbers down, maintaining the structure but rearranging what numbers go with what nodes, because we're inserting something in between 13 and 26. Either way, that was at least linear time, even on the average case. And so what we would prefer to do is have some arrangement that was slightly faster than that. And so one thing we can do in this regard is to relax our restriction of a perfect skip list yet. So what we're going to be doing here is no more perfect skip list. From time to time, we might have MPs or exam questions that deal with perfect skip lists. So it's helpful to know how the structure of a perfect skip list is supposed to be. But in terms of real use, we end up not really having that perfect structure because it's too hard to maintain if we're going to do inserts or removes, as we've already seen. Even in the best case, we get linear time for insert and remove on a perfect skip list. What we will instead do is point out that if I have some sort of list, this would be the idea of a perfect list, where let's say I have my level 3 list, and I'd have here node 8, and node 16, and node 24, and node 32, and then maybe that points to null, depending on how many nodes were in this perfect skip list. However, you say non-perfect, what we could also say is realistic, because this tends to be how they are really dealt with in real programs. What we notice is the whole goal of that level 3 list was to make us jump every 8th node. The idea being then I could, if I had a pointer to here and a pointer to here, I could quickly, or a pointer to here rather, I could say, given this node, I can look at the next node and ask myself if it's worth jumping there or not. And we had some rule, actually let me change this, forget that. We start here, this would be, we can keep it. So if we're at this node, the idea would be we don't want to search all 8 of these items. So if those 8 items are all less than 16, or all less than what we're looking for, what we can do is notice that, well, if I jump to 16 right away, if I'm looking for, say, 20, or if I'm looking for what happens to be located in node 20, then what's located in node 16 is going to be less than that. I could jump here right away and skip having to individually, one by one, go through all those nodes, when we knew for a fact that if this was less than what we were looking for, then all these would be less as well. And if we can just quickly say I should jump past this node, why have to go through all 8 nodes there, or all the nodes here to do it? Jump from the 8th node to the 16th node, and then move on from there. Now, if we happen to be dealing with now nodes that are a little bit more spaced out, if, for example, instead we point to here the 7th node and maybe the 17th node here, and here we have 23, and here we have 30, and so on. Here I had, this is the 8th node, and then I had 9, 10, 11, 12, 13, 7 nodes before the next one, 7 nodes before the next one, 7 nodes before the next one. So it's every 8th node. If this is node 0, then I have 7 nodes, and then this is node 8. 7 nodes here, and that's node 8. Here, I had 9 nodes before this one, then 5, then 7, no, 6. Maybe if I had gone to node 40 here, maybe I go to node 40 again, but now I've jumped 9 nodes in between. So here, 9 more nodes, and then this would be the 10th node. So here I went every 8th node, 8 more, 8 more, 8 more, 8 more. Here I went 7 nodes, then 10 more, then 6 more, then 7 more, then 10 more. So in the bottom list, we don't exactly skip every 8th node. Sometimes we skip less than 8 nodes. Sometimes we skip more than 8 nodes. However, more or less, we still have the same idea. We're skipping about every 8th node. The point of this level 3 list was to enable us to quickly traverse down by jumps of 8, because there'll be a level 4 list above this that'll be jumping down by steps of about 16. And what we could do then is say, well, from that list, from that level 4 list, maybe this was a part of it and this was a part of it. And I could say, well, from this node to this node, maybe I say, well, whatever's in node 17 is smaller than what I'm looking for. Whatever is in node 30 is larger than what I'm looking for. And so I drop down to level 3 and start searching that, because I know what I'm looking for is between those 2 points in level 4. Now in level 3, 23 serves as roughly the midpoint of that list. We have 5 nodes and then 23 and then 6 more nodes, or 5 nodes and then the 23rd node and then 6 more nodes. So it's about the halfway point. Maybe sometimes it'll be a little bit closer to the left, maybe sometimes it'll be a little bit closer to the right, maybe it'll be dead in the middle. But whether it's dead in the middle or just close to the middle of the array shouldn't really be a big deal. It's like doing a binary search, where instead of finding the exact midpoint of the array, maybe I always find 4 cells away from the midpoint. And that's how we do my binary search. So what? We're still going to have about half the nodes on this side and about half there. Here we'll have a few fewer than half. There'll be a few more than half here. Ultimately, we're okay. And the same idea here. If the node at 17 had been too big, I've got here 6 nodes and then the 7th node and then 9 more. So I don't exactly have a perfect split here. In this case, I would have 7 nodes, the 8th node, and 7 more. Here, I've got the actual node the first node in my level 3 list is a little closer to the left than I'd like in an ideal world, but it really shouldn't make that much difference. Essentially, if my level 4 list tells me to search between these 2 points, this is approximately the midpoint. And I get approximately half the nodes here and half the nodes here. And it turns out that if all these lists are dealing with giving us approximate midpoints instead of exact midpoints, that's really going to be pretty cool. We're okay. It'll be okay. We'll talk about the actual results of the analysis later on in the lecture. But basically, that's going to be acceptable to us, that idea. So that's how we get around this problem. That's the beginnings of how we get around this problem. What we're going to say is, listen, as long as I have, as long as I expect to have the proper number of nodes of each number of pointers, then I'm okay. And so we need some terminology to describe this so that we don't have such an awkward conversation about things. So we will say a level I node is a node with maximum level of I. So if I throw that other slide back for a moment, the one that we looked at the very beginning of this lecture and most of last lecture, the largest level here is 0, so that's a level 0 node. The largest level here is 1, so that's a level 1 node. This is a level 0 node. this is a level 2 node, this is a level 0, that's a level 1, that's a level 0, that's a level 3. 0, 1, 0, 2, 0, 1, 0, 3. So that's how we're going to define a level I node. We're saying a level I node is one where we're simply naming the level of the node for the maximum level pointer that that node has. And if you look at this list, what you'll see is that half the nodes in a perfect skip list, half the nodes are going to be level 0. We've said that whenever we draw out a list, be connected. Certainly all of them will have a level 0 pointer. This is, again, we're talking for the moment about a perfect skip list. All of them have a level 0 pointer. We said, though, half of them were also part of the level 1 list. All the even numbered nodes, or all the even positioned nodes. Node 2, node 4, node 6, node 8. Those are all part of the level 1 list. Well, if half of them are part of the level 1 list, half of them aren't. And of course, the way as we saw earlier, you can't be part of a level 2 or higher list unless you're also part of level 1. We don't suddenly have a node that says, well, I've got, level 0, no level 1, but I am part of level 2. We don't do that kind of thing. So, pretty big. We don't do that. If it's not part of level 1, it won't be part of level 2 or higher. So, since half the nodes are part of level 1, half of them aren't. And so the rule we get is half the nodes are level 0 nodes. Half of them are level 1 or more, half of them are just level 0. They're level 0 nodes because the largest pointer is level 0, and that's what we're saying here. Half the nodes have no pointer higher than level 0. Now the level 1 nodes were every other, or the ones that were at least level 1 were every other node. And then when we had level 2, they were going to be, well, we were going to point, we'd be here and here. I got kind of a goofy picture in the way now. But anyway, we expect that the level 2 nodes would be half of the level 1 nodes. So I can say half the nodes are level 0, half of them are level 1 or better. Out of all those that are level 1 or better, you can say half, and I shouldn't say better, half are level 1 or higher, and half of those are level 1 exactly. Just like when we said, given the entire list of level 0 nodes, half of them are also, the entire list of nodes in the level 0 list, half of them are also in the level 1 list. Likewise, given the entire quantity of nodes in the level 1 list, half of them will also be in the level 2 list. But if half the nodes in level 1 are also on level 2, that means half the nodes in level 1 are not in level 2. Just like we said down here, if half of these are in level 1, half of them aren't. Likewise, if half of the ones are in level 2, half of them aren't. And so half of the ones that are level 1 or higher are exactly level 1 and are not part of the higher list. And that means 1/4 are level 1. And indeed, we would expect that to continue. You can say half are level 0, 1/2 greater than level 0. Out of those, half are level 1, half are greater than level 1. 1/2 times 1/2 gives us 1/4. Out of the ones that are greater than level 1, half of them in a perfect skip list will be level 2. 1/2 will be greater than level 2. 1/2 times 1/2 times 1/2 is 1/8. So we say half of the nodes are greater than level 0. Half of them are also greater than level 1. and half of those are exactly level 2, and that's 1/8 total. And here we can say half are level 3, half are greater than level 3. And the ones that are exactly level 3, well, half of them are greater than level 0. Out of those, half are also greater than level 1. Out of those, half are also greater than 2. And out of those, exactly half are level 3. And so we can say, well, that's 1/16, and so on. We say half the nodes are level 0, a fourth are level 1, an eighth are level 2, a 16th of them are level 3, and so on and so forth. Now, we're not saying that only a 16th of the nodes are on level 3. We've already said an eighth of them are on level 3, because the level 3 list is every eighth node, or approximately now what we're saying. What we're saying, though, is 1/16 of the nodes will be exactly level 3. Another 1/16 of the nodes will be greater than level 3. There'll be 4 pointers or level 4 pointers or higher on them as well. But those are part of level 3 as well. We're just talking about where they stop. Half the nodes stop at level 0. A fourth of them will stop at level 1. An eighth stop at level 2. A 16th stop at level 3, and so on and so forth. Up until the maximum number of levels at that point, we're down to just one node. So if we were to able to generate nodes in those proportions, we'd expect we'd be okay. We would expect that if I create a list, let me mark 8 positions down. I'm not going to really draw much of the formal list here. Let me just draw in 8 positions. If I were to say, let's make that one a level 0, and that a level 0, and that a level 0, and that a level 0. And let's make that a level 1, and that a level 1. And this can be level 2, or let me make that level 3, and that could be level 2. So we could connect things like this. We, again, of course, have everything on level 0. The level 1 list doesn't quite go every other node, but it does skip over, skips over one node or skips over a few nodes. The level 2 list doesn't quite skip over every 4th node, but if you took this out to the long run, again, it's hard to show with just eight nodes here. But here we skip over between level 2 nodes, between nodes on the level 2 list, 1, 2, 3, 4, 5. We said 5 nodes later is the next level 2 node, rather than 4 nodes later. Big deal. Now maybe we only go 3 nodes to the next level 2 node, or next node in the level 2 list. Likewise here, we hit this node after only 2, but then we skip over many of these. And so maybe now we have 8 or 9 nodes to the next level 3 node. The idea here is, no, these proportions are no longer exact in terms of I don't have exactly every other node being in the level 1 list and every 4th node being in the level 2 list. But as long as I get the numbers right, as long as I have about half of them being level 0, and I do, 4 out of the 8 are level 0, just as before. 2 out of the 8, 1/4, are level 1, just as before. 1 out of the 8, 1/8, are level 2, just as before. And then, when we're at the top, we have just kind of an extra node. But if you kind of take this, if you have, 256 nodes in your skip list, expect 128 to be level 0. You'd expect 64 to be level 1. You'd expect 32 of them to be level 2 and stop there. You'd expect 16 of them to be level 3. You'd expect 8 of them to be level 4, and so on. And you don't really care how those are distributed among the list. It's not a big deal. I mean, you expect a relatively decent distribution. If I don't have the level 0 nodes occurring in the exact odd positions, it's not a big deal to us, as long as they're roughly equally distributed, which we would expect. And the larger the list gets, the more we expect that. Just like if you roll a dice, 6 times, you may not get one of every number. You may not get a 1 and a 2 and a 3 and a 4 and a 5 and a 6. But if you roll the dice 600 times, you expect you'll have roughly 1/6 of the times you get each number. And likewise here with the skip list, over small clumps of it, things might seem a little odd. Over a large skip list, we will expect the level 2 nodes to be occurring about 1 every 4 nodes. Just like if you have release a bunch of nitrogen molecules into a vacuum or into an empty room. Over time, you expect they kind of disperse among the whole room. You don't expect they're going to stay clustered in some corner. That's just not how physics works. And likewise with these nodes, just in terms of distributions, as we start saying I insert into random places and remove from random places, and whenever I insert, I'll create a node and I'll create them in these proportions, what we expect is that we will have, what we will get is that we have a pretty even distribution. That about 1 out of every 4 nodes will be at, or about every 4th node will be at level 2 in the level 2 list. About every 8th node will be in the level 3 list, and so on and so forth. So the question then becomes, how exactly can we get this arrangement to work? Because it's not always necessarily clear how we might generate these kind of proportions. What I want to do is to say, when I insert a value, I'm going to say, well, now that it comes time to insert here, we will generate, I don't want to quite say random, but there's going to be it won't be completely random, it'll follow these proportions, but we will use randomization to generate the level for that node. And since we expect that over the long run, our random selection of the levels is going to work for us, or a randomized selection will work for us, I expect that I won't always, every time I insert, get a level 0 node. What I'm going to expect is that when I say, okay, time for a new level for this node, I expect that half the time it'll be level 0. And 1/4 of the time it'll be level 1. And 1/8 of the time it'll be level 2. And 16th of the time it'll be level 3. And so on. And so then I'll go ahead and insert the value here, and I'll change the 4 appropriate pointers. So if it happens to be level 3, for example, by sheer quirk, then I need to change this pointer, this one, and this one. If it happened to only be level 0, I'd only need to change that one. Of course, plus setting whatever pointers are in the new node itself. So that'll be the idea. And we can accomplish that by simply using this formula. Level equals 0, x equals, and we'll do a rand selection here. This gives us a random number between 0 and 1. This is just pseudocode. And then we can say, as long as x is less than 0.5, we'll say level plus plus, x equals rand. We have something in here too to make sure we don't exceed the maximum number of levels, but that's the basic idea. If x is greater than half, we'll stop at level equals 0. If our random selected number between 0 and 1 is less than half, then we will increase the level to 1 and pick again. Half the time the level stays at 0, half the time it's incremented at least to 1. Out of those half of the times that it's incremented at least to 1, we pick again. Half the time that number will be greater than 1/2 and we'll stop. Half the time that number will be less than 1/2 and we'll increment again to level 2. So out of the half of the times that we go up to at least level 1, half the time will stay there, giving us 1/4 of the time total, and half the time we'll move up to at least level 2, 1/4 of the time total. And so on. So what this will do is 1/2 the time we'll get 0 for our level. 1/2 the time we'll get greater than 0. And when we have greater than 0, 1/2 the time we stay at 1. 1/2 the time we have greater than 1. And out of those, so that's half the time we're greater than 0, of those times we stay at 1, there's our 1/4. Half the time we're greater than 0, half the time we'll go even further than 1, that's 1/4 the time that we go even further than 1. And likewise, this will similarly split. Out of the times we go further than 1, we're at 2 or greater, meaning half the times we stay at 2, 1/8 of the time total. Half the time we'll move past 2 to 3 or greater, and that'll happen to 1/8 of the time total. So we'll get 1/2 the time we stop at 0, 1/4 of the time we stop at 1, 1/8 of the time we'll stop at 2, and so on and so forth. What we're essentially doing here is flipping a coin. It's like saying, okay, I start with level 0, and I'll start flipping a coin. And as soon as I hit heads, I stop increasing my level. As long as I keep hitting tails, I'll keep increasing it. So if level is 0 and I flip a coin, I get heads half the time I stop at 0. On the other hand, when level is 0, I flip a coin, I get tails, I could increase it to 1. So half the time I'll increase it to 1. And then now, depending on another flip of the coin, we either stay at 1 or we increase to 2. And if we increase to 2, then depending on another flip of the coin, we either stay at 2 or increase the level to 3. But it becomes increasingly unlikely that we have higher levels because, you can imagine if you flip a coin over and over and over again, it's unlikely you're going to keep getting tails over and over and over again. And likewise, it's equally unlikely we're going to keep getting numbers between 0 and 0.5 and never get a number between 0.5 and 1. If I'm randomly selecting numbers, I don't expect to always get numbers between 0 and 0.5. So, that said, I expect that to have with decreasing probability to get higher levels. I'll get level 0 half the time, level 1 1/4 of the time, level 2 1/8 of the time, level 3 1/16 of the time, level 4 1/32 of the time, blah, 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 blah. And so, therefore, in a list of 256 nodes, therefore, I would expect 128 level 0 nodes, because I'm getting level 0 node, I'm randomly generating a level 0 node 1/2 the time. 1/4 of the time, the node level I generate will be level 1, and so that'll be 64 out of 256 nodes. 1/8 of the time, the node level I generate will be level 2. That happens 32, 1/8 of the time, or 32 out of 256, and so on. And so what happens here then is the expected performance is going to be, we have random number generation works, I should say randomized. Randomized level number generation works as expected. And we expect distribution to be as expected. After all, this is expected performance. We expect the randomized level to be, half the time it's level 0, 1/4 the time it's level 1. I also don't expect, when I say distribution to be as expected, I expect these things to be scattered various places in the list. So it's not enough just these are the two things. We want to have the randomized level selection be correct. We don't want all level 0 nodes. In addition, we want the distribution of these. We have an expected case of the distribution. I don't expect I'm going to say, well, yeah, you've got 1/8 level 3 nodes. Or I'm sorry, 1/8 of the nodes are level 3 or higher. But they're all crammed at the beginning of the list. And then at the end of the list, you only have small nodes. We don't expect that. I do expect that not only will I have about 1/8 of the nodes will be level 3 or higher, but I expect they'll be occurring approximately every 8th node. That they'll be equally scattered throughout the list. Just like if you have a bunch of nitrogen molecules in a room, they're equally scattered about the room as they float in the air. They're not, you don't have, all the gas molecules crammed in one corner and everything else is a vacuum. If that was how the world works, you couldn't breathe when you walked in a room. You can breathe because the whole room is full of oxygen, and if I was to release some perfume or something, some cologne or whatever, at the beginning, at the door, eventually that scent would be something you could smell way down in the bottom of the room, because it would eventually kind of make it, the molecules would spread out and make their way throughout the entire room. That's how we expect things to work in the real world. And likewise here, we expect that as we're doing various inserts and moves in various places, we will continue to have, it would be very bizarre for all the level 3 nodes to somehow congregate at the beginning of the list. We expect that they'll be scattered evenly throughout the list. We expect the level 2 nodes will be scattered evenly throughout the list. The level 1 nodes will be scattered evenly throughout the list, and so on. Provided we get that expected situation, that our randomized generation works as expected, and the distribution of these nodes, we have the proper nodes in the proper proportions, and they're also distributed through the list as we expect, then we have log n performance for find, insert, and remove. Basically, we're saying if the distribution is as we expect, approximately distributed well, and the levels are the correct numbers, then we don't really expect there's any significant difference between this and the perfect skip list for find. We're saying, okay, it's not quite perfect. Now some of these things you're looking at are not the quite midpoints of the sublist. They're maybe one node off. So what? It doesn't really matter. So we'll continue to get log n for find if the list is all arranged as we expect, because the expected arrangement and such of the list will be pretty close to a perfect skip list. Insert and remove are now log n as well, because you can find where you're supposed to insert and then just generate a random level and insert there. I say, okay, I do a log n find to determine I'm supposed to go here, and now I insert there, no problem. And as I'm doing a find, I would keep track of, okay, this was the last level 3 pointer. This, wherever this pointed to was too big. So I keep track of the last level 3, level 2, level 1, and level 0 pointers, or what nodes they were in, so that when I insert, I have the nodes containing those pointers ready to change. So as I do a find, I'm going to have to go from level 3 to level 2 to level 1 to level 0 anyway. It's worth our time to keep track of, this was the node that held the last level 3 pointer I looked at, the one that pointed to the too far node. And this was the node that held the level 2 pointer that pointed to the too far node. And this was the node that held the level 1 pointer that pointed to the too far node, and so on. That means that if I end up changing this to, if I end up inserting a level 3, these would be the pointers I need to change. Here, 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 and here. So I keep track of this node is my level 0 node that I'm inserting after, and this would be the level 1, 2, and 3 node that I'm inserting after. So we want to keep track of that as we do our find. Once we do, then insert is simply a matter of finding in log n time where it goes, and then doing our random generation to kind of get the level, and then inserting properly. And the insertion, once we have these pointers, is just going to be log n because we're just setting a number of pointers. And there's log n of them, so you set log n pointers. Log n to find where the insert goes, constant time to figure out how tall the node is, and then logarithmic time to assign the pointers to put the node into the list. And likewise with remove. So I expect if the list is as well proportioned as we expect, then we would expect logarithmic time for find, insert, and remove. This will be a fast log constant, logarithmic n, and it will be very, very, very likely. Sometimes you say your average case is not, that's kind of what you expect, but the worst case can happen. Here we really, really don't expect the worst case to show up. In the worst case, it is indeed order n for all 3 if node proportions are way off, which we don't expect if our algorithm is randomized, or if the distributions of a correctly proportioned node set of the list are way off. And we don't expect that in real-world data either. But if we've got nodes allocated in the wrong level proportions, or if we have nodes allocated in the right level proportions, but they're distributed wrong throughout the list, all the level 4 or higher nodes at the beginning, and no level 4 or higher nodes anywhere past the first quarter of the list, then if there's a continual problem in that regard and all over the list, then those would be our worst case situations. Both of them are extremely unlikely. So this expected performance is pretty much what we are going to see. And in very rare circumstances, we might hit a worst case performance, which means if you absolutely cannot tolerate worst case performance in any situation, then this would not be the structure for you. If it cannot be linear, absolutely cannot be linear under any circumstance for whatever reason, that's critical constraint of what you're doing, then this would be a wrong choice for you. But if you're willing to say, I can handle, if every once in a while a bizarre, a poorly performing skip list, as long as in general things perform well, then this is a very nice structure because we really do expect, in almost all cases, we're going to get the expected performance. And in fact, this can be a little lower than an AVL tree in terms of constant factors because the AVL tree uses recursion. And if you're going to try and write an AVL tree without using recursion, it'll be a hideous mess. You can try, though. You're welcome to do so. But if you're going to write an AVL tree using recursion, then we expect the constant on skiplist to be a little bit lower. And so skiplist performance can be nice. And you'll see the book makes some odd mention about how skiplist implementation can be easier than balanced binary search tree implementation in some languages. We're talking there about not recursion. And so if you're going to try and implement an AVL tree without using recursion, it's going to be very, very nasty. And so if you're making the choice of whether to write a skip list or an AVL tree in some language, and you don't really mind a very, very unlikely worst case, then yeah, that, if all else is equal, if you say, listen, I don't really mind an unlikely worst case, and so I can either write a skip list or a non-recursive AVL tree, and the non-recursive AVL tree is a lot harder to write than the skip list. And that's what the book's referring to. However, normally you'd want to use, you could use recursion, so that wouldn't be a problem. But if you're going to use, if you for some reason don't want to use recursion, then you can say, well, the AVL tree might be a little faster if you optimize out the recursion, but the skip list gets close to even a non-recursive AVL tree performance without, and would be easier to deal with. Not that I really believe easier to code is an acceptable metric, but that's an academic standpoint. And sometimes in the real world, if things need to be done today or whatever, then sometimes those kind of decisions can influence things. As an academic, we say, you shouldn't say easier to code and have that be a legitimate metric. But in the broad software engineering principles, the ability to create a fast prototype of something might be a legitimate concern. And so if you happen to have, no AVL or skip list code on hand, you may decide, well, it's worth my time to write something faster. But on our exams, that won't be an acceptable metric to choose between things. But I'm letting you know, in the real world, fast prototyping can be, a legitimate factor. But we don't want you to think about in those terms right now. We want you to understand the structured trade-offs. So, but anyway, the point is here, skip lists are close in performance to a binary or to a balanced binary search tree. The memory usage will be the same as well, because if you add up the number of pointers, it comes out to 2 times the number of nodes. It's a geometric series. Half of them have 1 pointer, a fourth have 2 pointers, a eighth have 3 pointers, a 16th have 4 pointers, and if you add all that up, you get about two times the number of nodes would be your total number of pointers. So anyway, that's skip list. I think I actually took way more time on that than I intended to, so this lecture will probably be a little bit longer, even though I said it would be a little bit shorter. Those of you who are dealing with these remote videos are probably used to by now that I always intend to run a little bit longer than I mean to. I elaborate a bit more since it's on video. I don't have a bell to worry about, so hopefully you're cool with that. If you're fuming and irate that they take 55 minutes rather than 50, then let me know, I guess, and I'll try and be more careful about that. At any rate, the other thing for us to worry about, and this will be a very short, quick discussion, is the idea of a bit vector. And this requires a certain thing, that your type is enumerable. That is, you want to be able to lay a set of indices 0 through some finite number minus 1 as indices for your set of possible elements. For example, take the days of the week. We have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. 0, 1, 2, 3, 4, 5, 6. This is an enumerable collection. There's a finite number of elements, and I'm able to assign them the numbers 0 through 6. Now, on the other hand, consider the set of all strings. How do you begin to enumerate all strings? You don't even know, you don't know how long they are. If I said all strings with 3 or fewer characters, then maybe I can enumerate that set. But to say all strings, that's an infinite set. No, I can always have longer and longer strings, so there's no way to enumerate that. Certain languages will provide facilities for easily enumerating values. Certain ones won't. C++ does. The idea, though, here will be that the reason this enumeration is important is because what a bit vector will do, dealing with a bit vector, what we're dealing with here is an array. We'll talk about the implementation in a moment, but conceptually what we have is an array of bits. Where each of these array indices corresponds to one of our elements. So remember, 0 was Sunday, 1 was Monday, 2 was Tuesday, and so on. That's why we want to be able to enumerate our values. Well, we want to be able to quickly generate the index given a value. And so when certain languages provide enumeration features, the word Sunday can stand in for the number 0. It's sort of like becomes a variable. Sunday becomes the name of a variable that holds the number 0 in a sense and serves as the index 0. Likewise, Wednesday would serve as the number 3. So we can use the values themselves as integers, and that's the idea of enumeration. We're saying take this collection, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, treat each of those as an integer variable. Quickly enumerate these to be the numbers 0 through 6. Now, I can say if I want the set Monday, Wednesday, Friday, which is when CS225 meets for lecture here in Urbana, I can have 1s here for Monday, Wednesday, Friday, and 0s for the rest. That is, I have 1 for elements in the universe of elements that are in the set, and I have 0 for the elements in the universe of all elements that are not in set. The universe is a term from set theory that you're hopefully familiar with. It just means our entire possible collection, which in this case is a finite collection of 7 values, Sunday through Saturday. If you said all strings, the universe is a set of all possible strings, and that's an infinite set. So we say here, certainly the universe then is finite because otherwise the universe of elements wouldn't be enumerable. And what a bit vector does is it represents the entire universe of elements. We have 1 bit for every conceivable element that might be in this set. And the bit is set to 0 if the element is not in the set, and it's set to 1 if it is. And so that's how we got that. We have Monday, Wednesday, Friday set to 1 because Monday, Wednesday, Friday are in the set. And the other elements are also represented. Sunday, Tuesday, Thursday, and Saturday, we stored 0s for those. That's the idea of a bit vector. It's a vector or an array of bits. So given that, what we're dealing with then is the fact that we can have lots of operations work very quickly. For example, if you want to insert x, you simply say a of x equals 1. Say, well, whatever I'm passing in, I want to insert Saturday into my set. I say, well, that's easy enough to fix. 0, 1, 2, 3, 4, 5, 6. I had 1, 1, and 1 here. I want to insert Saturday into my set. When I insert Saturday, I say a of Saturday is 1. And since Saturday has been enumerated as 6, we're really saying a of 6 equals 1, and we do that. Likewise, if I want to remove a value, I can say a of x equals 0. So if I say, no, actually, I shouldn't have Saturday in there, I can change that back to 0. And then is member, which would return, true or 1 if the x is in the set, and false or 0 if it's not in the set, I can say return a of x. If a of x is 1, I'm returning 1, and that indicates I'm in the set. If a of x is 0, then x is not in the set, and I'm returning 0. And all those are constant time. So provided we have a bit vector, we can get insert and remove and is member to work in constant time, which is very nice. We have a condition on this. We have to be able to enumerate the values, but we can, provided we can enumerate the values in the universe. So it's not practical for the set of all integers or the set of all strings, but some data sets it would be practical for, that they'd be finite sets. we can then have insert and remove and ins member work in constant time. In addition, we can have, this won't be completely accurate, but for now we'll say we can. I'll talk about it more in a couple minutes. We can have set operations like union or intersection work in constant time. And we can do this through bitwise operators. So let's say I have 3, 4, 5, 6, and 7. And normally I can't address a machine anything smaller than a byte, 8 bits. So I may say, okay, this is my set, the set of days of the week, Monday, Wednesday, Friday, Sunday, Tuesday, Thursday, Saturday, and this cell we don't really care about. It's along for the ride because we can't do anything on anything smaller than a byte, but we're only looking at the first 7 bits in this case. So that's the days of the week that CS225 lecture meets, and then let's say someone's got section with Adam on Monday, which is when he tends to tape the remote copies of the section. So we have, actually let me not do that because we've already got that element here. Let's say you have section on Thursday. So you'd have a 1 here in the Thursday value, and then this we don't care about again. So you have a 1 at A of 4. Now if we union those, this is a bitwise OR. We simply say, well, if I want the union of these, I can say, give me I'll have to write that a little lower. 4, 5, 6. Again, we don't care about cell 7. And we say, basically 0 or 0 is 0, 1 or 0 is 1, 0 or 0 is 0, 1 or 0 is 1, 0 or 1 is 1, 1 or 0 is 1, 0 or 0 is 0. The OR operation, it's true if either of them is true, or both. So now we have Monday, Wednesday, Thursday, and Friday being 1, the union of those two sets, and that's the day that this student would have 225 at all here in Urbana. You have lecture on Monday, Wednesday, Friday, you have section on Thursday. The union of those two sets is when you have any sort of CS225 class. And likewise, insertion would be a bitwise AND, or I'm sorry, intersection rather. Intersection would be a bitwise AND. I have the set 0, 1, 0, 1, 0, 1, 0, and then I say, well, I want to find out what days I have 225. No, let's say now this student has section on Monday, and this student is concerned about saying what days he or she has lecture and section. Well, then you're intersecting the set you have lecture and the set you have section. So you have all 7 bits there, and so the result of those is going to be just this set again, 0, 1, 0, 0, 0, 0, 0. The bitwise AND of those two gives you that result. And since these are actual machine instructions, you can do a bitwise OR or bitwise AND. You can do these in constant time as well. So that becomes the idea here is a bit vector will enable you to do set operations like union, intersection, and difference, and so on, and insert and remove an is member very, very quickly. Now, implementation-wise, we say, okay, use bitwise AND or bitwise OR for the implementation. It doesn't quite work out as cleanly as that because you could have more than 32 bits. And these days, machines are 32 bits. And so you say, if I happen to have a 48-bit vector, I have to divide it into 32 bits and 16 bits. And likewise, so if I'm trying to find the union of two 48-bit vectors, I'll need one machine operation to get the first 32 bits of my result, and a second machine operation to get the next 16 bits of my result. In reality, what we're saying is the union and intersection time is n over 32. You go of n over 32 where n equals size of your vector. As you go to a 64-bit machine, then it's n over 64. In other words, the larger your machine word is, the more bits you can compare to each other using a bitwise AND or bitwise OR instruction. And so machines that have 32-bit pieces of data that it performs instructions on, you can do 32 bits at a time. Machines that can do 64 bits at once, then that would mean that your time would be the total size of the vector divided by 64. Which means if your vector gets really, really large, like in the millions, then it sort of becomes linear time anyway for these operations. But typically, bit vectors are not that large. We'd end up with an operating system trying to keep track of a bunch of flags for various conditions or something like that. So you can have often small universes of data, 16 bits or 16 elements or 32 possible elements, or even if it's 100 possible elements, this wouldn't take any more than 4 machine instructions on a 32-bit machine. So it's only as bit vectors get really, really large that this starts to come into play. As long as they're like 100 cells or less, effectively we can, in 3 or 4 machine operations, do a complete union of 2 bit vectors or a complete intersection of 2 bit vectors. And so it's effectively constant time. And so it starts to, the difference between our theoretical constant time and what we really have, which is linear time, starts to become noticeable as we get much, much larger universes. If the universes are small, then it's sort of a constant time operation. In other words, it grows pretty slowly at first. So that's the idea here. And the same thing sort of applies for insert and removal and such. We can't really index individual bits. So what we would tend to do is likewise use bitwise AND or OR bit masks for an implementation, at least in C++. I mean, you have shifting operators that enable you to take a bit vector and say, I want to shift it this way, which looks like the output operator because it serves double duty. But I can 0, 0, 0, 0, 1, 0. In other words, I can shift these bits this way and get that bit in the new position. You have shifting operators to shift the number, right or left. We'll talk about that actually a little bit in lecture 29 as well on priority queues. You also have the ability to sort of do a bit mask. So I can say, if I know, for example, that Wednesday equals 0, 0, 0, 1, 0, 0, 0, 0. And if you count from this direction, if that's the ones place, 2, 4, 8, 16, 32, 64, and that's the 128th place in a binary number, then this number is 16. That's 16 in binary. And so what I can do is say, if I have a set I don't care about this cell, and I have, say, the set Monday and Friday. And so we have here 0, 0, 0, 1, and 0. And I want to insert Wednesday, I can say, do a bitwise OR, do a union with the set containing Wednesday. 0, 1, which we've got here, 0, 0, 0, 0. And the result then will be 0, 1 from the top array, 0, 1 from the bottom array, 0, 1 from the top array, 0, and then we don't care about that one. Or in other words, I can say whatever I have here, treat it like a number, do a bitwise AND with 6, or bitwise OR with 16, and that's the equivalent of inserting Wednesday into my set. And so we can sort of view things that way, where our inserting of individual bits, if I want to insert Wednesday into my set, that's like saying union it with the set containing Wednesday. And if I can quickly generate this number from the value Wednesday, then I can quickly do a bitwise OR and insert Wednesday into my set. So conceptually, this is how we're doing insert or removal or isMember. Since we can't really extract individual bits out, we can only kind of deal with things in terms of bytes, 8-bit chunks in a machine typically, then the way we'd really implement these instructions would be sort of as a bitwise or a bitwise AND to sort of pull out the particular value we want and then figure out what day of the week it is, or convert from day of the week to binary number and then bitwise that with our set. So we can get these to work in that sort of pseudo-constant time, the order n over 32 time. But that would be how we would do it. So you'll use a lot of bit masking in that case. we're not going to ask you about those kind of implementations on the exam. It's better just to know what a bit vector is. Bit vectors are good when you are dealing with small sets, or if you had, small universes, or large universes and dense sets. So in other words, if you have a large number of elements that are possible, but most of them are in your set, then you're okay. When it's not good, when we tend to have bit vectors tend to be a poor choice, bad, not bit. Bad when you have large universe, sparse, i.e. small sets. Because we're representing a cell for every element in the universe anyway, so if we have a large number of elements in the universe and a very small number of elements that are actually 1, we're having a bunch of space for a bunch of zeros. And remember, we said that's when we want to use sparse arrays. When we have this array allocated and there's not much in the way of actual legitimate, useful, non-default data in that array. But making this a list instead of a bit array would defeat the whole purpose of the bit vector. So we tend not to have too good performance, or it tends to be more of a waste when we have huge numbers of spaces allocated for a large number of bits, and then most of those bits are 0. And then, as we said, it's impossible if set is non-enumerable. So this is just don't use bit vectors. It's not the wisest choice. It's simply impossible to use bit vectors at all if your universe can't be enumerated. So I can't say, oh, I have all the integers, because how do you have a set that has 1 or 0 for every possible integer? You can't. So that's bit vectors. There's not a whole lot more to say about them. Just basically know what they are and their good and bad points, and the idea that you could get this constant time performance out of them, or sort of constant divided by the machine word size, or n divided by the machine word size, I should say, which isn't constant for very large sets, but it's effectively constant for small sets. The whole thing about bit shifting and that is something that's useful for you to know, but we're not going to ask you to do it on an exam, so don't worry too much about that. That's it. What we will start next time for the next 3 lectures, which I'm going to be, of course, continue to be running off over all day today, is is hashing. So that's going to be the focus of the next 3 or 4 lectures, and I will see you in a few minutes, though it probably won't be a few minutes for you. Talk to you then. Bye.